Hello, I'm Hirley Alves, Associate Professor on Machine Type Wireless Communications at University of Oulu, and today we will be taking a look into Service Mode Coexistence. I lead the Machine Type Wireless Communication group, and within the 6G Flagship, I lead the Strategic Research Area 1 Team C Massive Wireless Automation. In the MTC group, we have a quite broad range of topics and areas. So we cover the Massive MTC, Critical MTC. We also have several applications of machine learning for MTC and some proof of concepts. Here are a few of the keywords associated with the group. For today's presentation, we will be focusing particularly on Cellular IoT and from the Critical MTC side on Dependability and predictive radio resource management. From the 80s to 2000s, the connectivity was focused on voice users. Then we moved to broadband connectivity, including data devices. And now we are moving forward to trillions of connected smart objects. What will come next is that we are becoming a digitalised society. So we focus on providing best connectivity from the third generation onwards to providing connectivity to several thousands of different devices, and now moving towards digital transformation through the metaverse and the digital twins. So we have evolved from these use cases and requirements. We are well familiar with this picture here, introduced in 2015, the three cornerstones of the 5G, the fifth generation. And in there we had the extreme mobile broadband, which was the extension for broadband connectivity, aiming to reach gigabit data rates over the air. But the most interesting part of this generation is the inclusion of massive machine type communications and critical machine type communication, also known as ultra reliable low latency communication. And with these two service modes, 5G dedicates 2/3 of its service modes to IoT. These two service modes, dedicated to machine connectivity, focus on extending the capabilities of the connectivity, so addressing millions of battery-powered devices, particularly in the massive case, and also attending the demands from the industry, reaching to millisecond latency and ultra-high reliability. We are seeing the evolution in the network. So for 2023, we already have a proposal for the 6G and usage scenarios, and we are seeing that these original three scenarios are expanding and merging the requirements from these different areas and creating a rise of new set of usage scenarios. Here we have a few, and as we can see, massive communication and ultra-high low latency communication are still present, and we are also expecting these service modes to push the limits of the physical communication over the air. Not only that, the ITUR is also proposing overarching themes such as sustainability, connecting the unconnected, and ubiquitous intelligence, for instance, as part of the use cases. As we can see, the IoT levels across a wide range of verticals. So in this particular setup, we have smart transportation, education, smart healthcare, traffic management, street lights, and smart home, smart farming. And not only cellular services will be used to provide the connectivity for all these different verticals, but also non-cellular solutions. Particularly today, we will focus on cellular IoT. So we expect a harmonious coexistence of the heterogeneous services from cellular and non-cellular technologies, but also within the cellular technology. So the coexistence of EMBB, Massive MTC, and Critical MTC. So in these following slides, we will first focus on the Massive MTC aspects, and we'll be looking into the works of two doctoral students, Eduardo Tominaga and Leatili Marata. First, we would like to understand what is the coexistence, what are the key aspects of this coexistence. We have this illustrative network where we have a base station and users from the different services. We have eMBB users, so broadband users. We have critical MTC users, ultra reliable low latency communication users, and we also have several massive MTC users. And the traditional way of doing this is through allocating orthogonally the resources. In this example, we have a grid where we have resource blocks dedicated for eMBB users in gray, and in blue dedicated for ultra reliable users or massive MTC users. On the right, then we have what we are calling non-orthogonal slicing or non-orthogonal coexistence of resources. So in this particular case, we allow ultra reliable users to share the same resources with the eMBB users. So this is shown to be efficient. We have observed that there is possibility to harmonious coexistence. There is certain trade-offs that we need to achieve. There will be some performance improvements by doing so. So we are able to reduce collisions and improve data rates for both users. However, we will have then to sacrifice extremely high rates for the eMBB user so that we can accommodate the ultra reliable user. On the other hand, when we have massive MTC users overlapping or sharing the resources, then we can accommodate a very large number of users up to a certain rate of the eMBB users. So we have a trade-off in terms of rate and number of users that we can accommodate. One interesting observation that we have from here is that increasing the number of antennas in the system helps to increase the data rates and also the number of users that we can accommodate sharing the same frequencies. So that motivated us to exploit further the usage of multiple antennas at the receiver. In this particular case, we are again looking at the uplink of a cellular network where we have devices that are connecting to a base station. And the focus of this work was to compare linear and non-linear receivers. And to do so, we compare different architectures and we allow them to integrate successive interference cancellation and parallel interference cancellation. We have seen here that we can increase the performance of the network by doing so, by allowing non-linear receivers, by doing successive interference cancellation, but the largest gains come by including parallel processing. So that's what we can see here in this plot on the left, where we have the outage against the target SNR, and we see that there is a substantial gain in terms of performance. However, there is a trade-off in what are the operational regions for these different receivers. And we also can see on the plot on most right that the average number of operations and inverse transformations is also reduced by including parallel processing. So again, the conclusions here highlight that having more antennas is an advantageous for the coexistence, and having nonlinear receptors are also an advantage for coexistence. Inspired by these results, we now move to a setup where we have a massive number of MTC users deployed over a given area and a base station with a large number of antennas, where the number of users is much larger than the number of antennas. Again, similar to the previous case, we allow the users, the massive MTC users, to overlap or share the resources with the eMBB users. And this is done such that we dedicate some pilot sequences for the massive MTC users, and the remaining coherence time is used for data transmission. Our aim here is then to take a look into the design of these pilot sequences to better exploit the non-orthogonality of the channel. Our aim here is to exploit non-orthogonal sequences and improve the connectivity of the massive MTC users. So we have here one expression, that is the received signal. We can clearly identify the EMBB sequences, and for that we assume that the EMBB users will use orthogonal pilots, and the Massive MTC users will be using a sequence of non-orthogonal pilots, and that is illustrated here in these two boxes. Since we know the pilots from the EMBB users, and they are orthogonal to the Massive MTC users, we can easily remove those from the received signal, and what remain is the signal from the Massive MTC users plus some noise and residual interference from the EMBB. So once we have this, then we can solve this problem by simple AMP-based detection type of algorithms. And we propose in this case two pilot allocations. So what are we calling non-orthogonal pilots here? We take from a matrix of orthogonal channels and we allocate some of those channels to the MBB user, and the rest of the sequences we combine them to generate the non-orthogonal sequences for the MTC users. So the MTC users and the MBB users, they are orthogonal, but any MTC user will have some correlation with other MTC users. But even though this correlation we are still able to detect, and by doing so we are still able to improve substantially the performance of the EMBB users and also the MTC users, as we can see here in these two plots. Also, as we increase the pilot length, the performance increases since we have more samples to estimate. So that is it. All in all, these results evince the importance of the pilot sequence generation. So that motivated our next work that I would like to highlight here. So we expand the previous work by allowing multiple EMBB devices, and we have an even larger network of MTC devices. Again, we will dedicate a portion of the time for pilot allocation and the remaining time for the payload. And again, we will be looking into the pilot sequence generation. So the received signal is similar to the previous case. Now we have more EMBB users. We still allocating orthogonal pilots to the EMBB users. However, the MTC users will be using a sequence of non-orthogonal pilots. And in here we have just transformation or matrix form of this expression. So in red we have the messages. In the matrix Dn is the activity of these MTC devices, and G is the channel, W is noise. So what we would like to highlight here is that the activity of these Massive MTC devices is a sparse matrix, which makes things a bit more complicated. So that's why we resort to sparse signal recovery in order to be able to recover these MTC users. And as in the previous case, we propose a pilot allocation strategy. In this case, we optimize the number of columns that we will be combining, so to generate the pilot sequences. And that combination, or this optimal number of columns that we'll be using during the combination, is shown here in this plot. And we can determine the optimal points for performance according to a given performance metric. In this case, we aim to minimize the collision probability of two sequences. So we determine how many columns do we need to combine in order to generate the Massive MTC pilot sequences. So now we can write this expression again in a more compact form. So S again is the messages or the sequences that we are transmitting, X is the combined activity in the channel, and W is the noise. So once we generate the optimal sequences, non-orthogonal sequences, we can move forward with the detection and decoding. So we propose this optimization problem, which we solve through a series of different methods. We applied approximated message passing. We also compare to the alternating detection method of multipliers, ADMM, L21 minimization. We also apply expectation maximization, sparse Bayesian learning, and we also compare to the simultaneous orthogonal matching pursuit algorithm. And these are the results that we have obtained. On the top, we have the normalized mean square error against the SNR of the EMBB user. As we can see, the proposed pilot sequences have an increased performance, and the performance increases even more as we increase the pilot length, particularly compared to Gaussian sequences. And we can see the difference between the performance of these different algorithms on the bottom on the left, where we have the probability of misdetection against the number of antennas. Again, another highlight, as we improve the number of or increase the number of antennas, we see an improvement in performance for all the algorithms. And on the right, we have again the probability of misdetection against the probability of false alarm. And we can see that there are some improvements, and these results are obtained for different levels of SNR at the EMBB user. So overall, we see that the coexistence is dependent on properly selecting the pilots and the pilot length, the activation probability, and the number of antennas. Next, we will shift gears and move to critical MTC scenario, and where we will be dealing with dependability via channel history. This is the work of Diane Perez. So in this case, rather to look at the uplink, we will be looking at the downlink. So we have several EMBB users, and we have one ultra-reliable user that needs a transmission. The base station will assign a slot and try to perform a hybrid precoder to serve this ultra-reliable user. We can see here in the bottom left the bandwidth and the time allocation for these different users and the strategies that are being used. The main difficulty in this case is to acquire instantaneous CSI. That is possible for the EMBB users, but due to the latency requirement of the ultra-reliable low latency communication user, we are unable to acquire instantaneous CSI. Therefore, we are using the channel history, previous transmissions, in order to design this precoder. We have here the signal Y. We can clearly identify the ultra-reliable component and the EMBB component. So we can design this precoder W so that we can improve the performance of the ultra-reliable user, satisfying its requirements as well as satisfying the requirements of the EMBB user. To do so, we pose this following minimization problem. So we are trying to find the precoder with the minimum power constrained to a reliability requirement, which is this first expression, and then the second expression is a SINR target that is designed for coexistence. So we can set and select these thresholds so to improve or have the coexistence of the ultra-reliable and the EMBB users. The main problem in this case is acquiring instantaneous CSI, which violates the latency. And the solution that we found was to use the channel history, samples from previous realizations. The way to do that is to use the Chernoff bound, as we can see here, which allows us to estimate the sample mean and the covariance matrix. And with those two information, we can then design the precoders. So in our design, we adopt zero forcing and transmit power minimization precoding with the SINR constraints. And we are able to see an increased performance in terms of reliability. So we relax the availability of having instantaneous CSI for the ultra-reliable user, and by using the previous realizations from the sample, we are able to design efficient precoders, as we can see from these two figures. On the left, we have the outage probability against the target SINR, and on the right, we have the transmit power. And as we can see here, we can guarantee levels of reliability, for instance 3 S's and 4 S's for the ultra-reliable user, and we can see that the performance for a target ISNR of 10 dB, we have around a 20 dB M transmit power. So by exploiting this feature and the availability of the previous samples of transmissions, we are then able to harmoniously coexist ultra-reliable users and EMBB users. So we discussed a few alternatives of coexistence of EMBB services with Massive MTC and Critical MTC. In what follows, we give a brief overview of future research directions on this topic. For instance, moving forward, we are not yet clear on what architectures we will be using to support these stringent requirements. Self-read or distributed massive MIMO has emerged as one of advantageous alternatives due to the macro diversity gain, the signal sparse diversity, and its performance over regular traffic conditions. It's important to highlight that there is a trade-off between the beamforming gain and the macro diversity gain. In exploiting the channel history, one important feature is that we need to acquire these samples and store them, so creating a dataset for exploiting these different users. And the more samples we have for the estimation, the better will be the predictors. However, we could perhaps use machine learning solutions, for instance meta-learning, in order to reduce the pilot transmissions and still have the same target reliability and prediction accuracy. On the Massive MTC side, we have shown that the proper design of non-orthogonal pilot sequences and detection and decoding mechanisms is very important when we want these services to coexist. So we need to further look into this and have better ways to do the non-orthogonal pilot sequence generation. And I would like to thank you for your attention. Bye bye.